Everyone, thanks again for sticking around. And now you need to switch your brains back around a bit more again. We're going to talk a little bit about science on the surface of the moon. And I think yesterday someone mentioned you got to start every slide off or every talk off with an image of what you're going to be talking about. So mine is about water on the moon, and that is the image of water on the moon. That's right. You really can't see the water on the moon I'm talking about. We're looking at many parts per million surface adsorbed and surface water itself, which is different than water ice. But what I want to hopefully get to you guys today is the possibility that it might evolve. To this extent, it might evolve and migrate to the poles of the moon. If we did have thermoinfrared eye or infrared eyes, we might be able to see something like this, right? In this case, you do have a several hundred ppm up at the poles, and you have a diurnal variation there in the equator and mid latitudes. And it's that diurnal variation that has been observed since 2009 that we're still trying to understand. And to do this, we're looking at the spectral characteristics in the infrared right at 3 microns. So I warned you we're going to be talking about spectroscopy, and this is the beginning of it. This slide is again wavelengths on the bottom, 3 microns, normalized band depth on the left side. And this shows the different forms of water that an infrared spectrometer could detect. It's a mixture of actual data from the laboratory and reflection spectra, which would be the 2 lines showing OH and then H2O, and then water and ice. Those are models. It's important to understand that the models themselves aren't actually a reflection spectrum. If you had ice, you're also going to have adsorbed water and everything else, and sometimes all these all merge together. It's not necessarily that easy to tell them all apart. But when there's just OH, it is pretty easy to tell apart, regardless of the mineral that it's adsorbed to or in. And this is the case for the surface of the moon. And this is data from the epoxy or deep impact spacecraft that was repurposed to look at the surface of the moon. It has a 2.8 micron band. Again, the bottom axis on each of the 4 figures in wavelengths, and the bottom of the absorption band is around 2.8 microns. It's been normalized. An important takeaway is the 2 on the left is a moire, a pyroxene-rich material. And you can see the circled area in C. That's a small absorption band of the same area that's much deeper absorption band. So during the noontime, warm temperatures, there's shallower absorption band. This also occurs in the Highland materials. The 2 plots on the right and D, you can see that some areas have a more shallow band than the other. This has been interpreted directly without any reason to question why, that this is a change in the actual abundance of the water itself, or the OH. What I'm going to be talking about today is that by itself doesn't make complete sense. There's a numbers issue in terms of the abundance of solar wind that's needed to replenish the hydroxyl on the surface. And instead, I've been looking at a photometric explanation for the changing depth of the absorption band, at least as a partial explanation, to help the numbers, so to speak, work out. Okay. And this is an example of the numbers that we're talking about. You probably can't read them, but this is from the M-Cube instrument that goes from 500 to 3,000 nanometers or 3 microns. Spectral modeling by Schweilich and others have shown that these variations in the absorption band intensity are indicative of a few hundred ppm coming and going over a diurnal timescale. All right. And this is due to the presence of solar wind, which is dominated by protons primarily. Yeah, there are other particles in it, especially, but protons and very, very slow electrons, mainly protons. But there's other processes occurring which affect things, such as UV that hits the surface can photostimulate, photosputter water that's present there. There's also cosmic rays that go deep. More importantly, we have micrometeoroid bombardment that actually can do chemistry, and I'll just speak to that very quickly, in the surface of grains that have been planted with solar wind. So it's a very complex surface that we're dealing with on the moon. And what we're addressing here is just a small component of that, which is the signature of OH formed through the implantation of solar wind protons, right? Which, by the way, are by definition just in the rims of these grains themselves, because the protons only penetrate about 15 nanometers. That's shown in the schematic on the left. The scale bar, I mean, it's a cartoon, right? 15 nanometers. Due to thermal diffusion, they can reach 50 to 100 nanometers. And that's on order of the amorphous rim that's commonly seen in the grains on these, in the lunar sorrels of the picture on the left. The outer part, maybe it's hard to tell, but it says rim is about 100 nanometers in thickness. Compared to the grain themselves on the far right actual picture, that scale bar is about 100 microns. You have 3 orders of magnitude. Hopefully you got that one right. Difference there. And that is consistent with what we want to talk about here for the evolution and the formation of the OH itself, where it starts with protons, and they can form, as you can see, they can just come in and form hydrogen or hydrides. They can combine to form H2. That can evolve out with the temperature, either as hydrides or H2. We thought previously perhaps H2O would leave to that mechanism, but modeling's shown that's probably not very likely, that there is instead most likely an intermediary step, which is due to micrometeoroid bombardment that would impact into these solar wind saturated surfaces, which basically incipient reduced surfaces, and in the 1,000-degree plume or so, you could have non-equilibrium chemistry, form water, form nanophase iron, form rutile, form everything that you actually see on the surface of the moon. It's a very nice explanation, right, for actual water. So what we mostly see on the illuminated moon is not that water, because that makes its way to the poles or is photodissociated, but instead is the OH. But still, the water is very important. It leads to the formation of water, which can migrate into the surface, eventually make it to the poles, and you can have a kind of a water cycle. To the extent that this can actually occur, and that is what I really want to talk about. To what extent does that OH actually change in abundance on a diurnal timescale? So here's a useful model to show a estimate for the kind of magnitude we're talking about in terms of how long it takes to build up a certain amount of abundance of OH. So this is local lunar time, i.e. time of day. It doesn't matter on the x-axis. It's latitude on the y-axis, moving from basically the equator up to the poles. And the color scale means blue, not much. Red means a lot of OH formed by solar wind implantation, and then migration in the surface. And there's a lot of accumulation at the mid-latitudes due to the fact that you can form it and it doesn't desorb very quickly, right? So one should not have much diurnal variation up there. And that is true. That matches what the observations from epoxy, et cetera, show. Not much diurnal variation up around 70, 80 degrees. One would also have red all the way up there due to H2O coming down, sticking, you form OH and all. So this is just one specific model, one process, doesn't describe the entire moon. But what it does show that after about 120 days simulation, you create about 10 ppm of OH that way. Okay, that's the number we're looking at for a multiple diurnal case of OH that's stable at those latitudes. However, what we're modeling in the diurnal variation of OH in the mid-latitudes, where it's shown blue, right, because they're not stable on the left side, is absorption band change that's consistent with a few hundred ppm, and that's a change just a couple weeks. So we have basically and this is also true not just for what was that, M cube that was orbiting the moon on Sanjian 1, but also from Earth-based observations from IRTF, which looked at very similar wavelengths. Again, few hundred ppm variation was being modeled, and this is much more than a 10x. It could be 100x inconsistency between the two. So how do we resolve this? Is the modeling wrong? Maybe the modeling is wrong. Maybe it's actually much less, right? The amount of protons that are available, that's known. You know, it's 10 to the 8 protons per square centimeter per second. That is well known. So the question is, how can we resolve that dilemma? So what we focus on, well, what you can't see because it's invisible, like the water itself is invisible in the first image I showed you, is that those lines, right, they're actually implanting or going into various grains that have rims of OH on them. So you can imagine, if you can imagine grains with the little rims of OH on them, when you're looking at a low incident angle, you're penetrating the rims more, right? High incident angle, you're penetrating more into the volume of it, and you're having more sampling the volume of the grain rather than rims of the grain. There are two different models that we explored both theoretically and through experimentally, and that is for the presence of hydrated grains or hydrated rims on grains, uniform, basically infinite depth. And another cases where you only had multiple layers and 1, 2, 3, 4 layers of grains that are hydrated on it. The second case would be the example where the OH is stable, right? Wow. And the third case is where the OH is, and the first case where it's not stable. So, all right, I just talked about that right now. So we're going to, we also, as I said, attempt to model both scenarios. Summary, we couldn't reproduce the results. Like there was no variation with the illumination on grain thing, which made us not even think much is going to come from these experiments. But we did a careful experiment using well-characterized simulants. We picked some that had absorption band here at 2 microns, because we can't use 3 microns very easily, but that's a fine proxy. And we use a goniometer, so we could explore a range of incidence and emission angles. We explored 1, 2, 3 layers of hydrated grains, as well as all hydrated. We had SNR noise issues, of course. You often do in the first ones, but we were mapping the absorption features, see at 1900, right there, nanometers, quite effectively. And you see on the left side, upper left, 1 layer, 2 layers is thicker, 3 layers is more. Fully hydrated 3 layers look about the same. Now, it's hard to tell here. When we plot them out, if you look at the very top one, the triangles, you actually do see a pretty nice trend going from about 12% to 15% absorption band depth. There is clearly a dependency on incidence angle for the depth of for the depth of this absorption band. This did not show up in the 1, 2, and 3 layers, perhaps due to noise, but it's very suggestive that there is a photometric effect, but it's not strong enough. And I'm going to skip through some other things. And just end with photometry can explain at least some of the diurnal variation in the infrared. But overall, I'd say that we still do not understand this diurnal variation. The numbers don't quite work out, and we have more work to do on it. So that time is up. We can continue to read these, and hopefully at LPSC, we'll have a more full answer to understanding this diurnal variation on the surface of the moon. Thank you.
We still have room for a couple of questions.
Hi, great work. Some of the work that has been done on impact glasses from the Chang'e 5 mission.
Yes.
You might be aware of the work where actually there is a profile across those glassy grains where you see a diffusion profile for hydrogen. And I wonder, and then at the same time, the isotopic composition of that hydrogen suggests it's of solar wind origin. So the speculation is that there is some diffusion that's happening, and this is beyond tens of nanometer. We are talking about tens of micrometer here. And I wonder some of those diurnal variations that actually are reported, whether there is any contribution from diffusion-induced hydrogen in addition to what you are saying, direct solar contribution. Yeah. Is that possible?
People have talked about the possibility that, yeah, it being hydrogen can diffuse from grain to grain and form ephemeral OH. As long as that is not more of a lossy process than the solar wind rejuvenating it, that could account for actually some of it, right? Absolutely could. That should be looked into more. I would note that, yeah, we have some Chang'e 5 measurements there. And one thing Chang'e 5 did notice, or interpreted the paper correctly, is that the rock itself, the image of rock, right? It has an OH band at 2.8 microns, but the disturbed terrain where that was blown away does not have a 2.8 micron band in it. That implies that there is actually apparently no evidence or any solar wind produced OH that would have been in the near surface 2-3 centimeters down has since thermally evolved away. So that would be consistent with what you're saying is a migration. In that case, it's lost and not replenished, but on the surface, it could be partially replenished. So I think what you're talking about is consistent with, fully consistent with Chang'e 5 and perhaps our observations as well. Thank you.
One quick question. Hey, it's Craig.
Oh, hey.
Hey, I was just curious if you looked into the effects of grain size. So potentially differences in grain size would affect the thermal inertia, and you might get some differential heating.
Yeah, that's a really good question. So the grain size on the moon is generally pretty small, less than 100 microns. So we picked the finest grain size that we could, exactly for the reason you're talking about. You want to have more scattering, more sampling of the surface area when you have finer grains. You have a greater surface area to volume ratio for fine grain stuff. So we picked the finest grain stuff we could to make it as easy as possible to see the effect that we're looking for. So I'd argue this is probably the most best case scenario because we picked the finest grain. So I don't think we're going to look for grain size effects. It'll only get worse for us. We'd explain less and less if we did that.